In our previous lessons, we discussed the different mechanical circuits. We discussed the case whereby the circuit is free oscillation, or what you may call harmonic motion. You don't have any damping, you don't have any force applied. You simply have the spring, then the mass. We also look at the case whereby there is damping or damped motion. So here you have introduced a damper so that the oscillations are not just free. So you have a damper there. And we, of course, discuss the different types of damping. You have your mass. This, up to this point, you have not applied any force. Then we looked at the forced oscillations. For forced oscillations. So we saw that here you have your mass, you have your damper, but you also apply some, okay, you have mass, yes, and some force applied. And we derive the different types of equations and related some variables to the electrical quantities. So we saw that the force actually corresponds to voltage. We saw the impedance, mechanical impedance corresponding to impedance in the electrical circuits. We saw that the velocity would actually correspond to the velocity in the mechanical circuits actually corresponds to current in the electrical circuits. So we want to associate some of the variables again so that we may be able to appreciate how they affect the system. Because for most of us, you know, when you talk of current, we talk of voltage, when you talk of impedance, when you talk of power, you know how they relate to each other. So it becomes easier to relate them to the mechanical circuits and later acoustical circuits. So let's start with the simpler ones that we talked about in our last lesson. We talked of the free oscillation, or simply the harmonic motion. So we have that. We just have the mass, and we have Sm. And we saw that the equation for this is m d squared x by dt squared plus s of x equal to 0. So we want to compare this with an electrical circuit where you don't have a source, you have an inductor, then you have a capacitor. So we have L, then we have the C. So if we are to write down the equation for this circuit, you know that current in a circuit is given by dq by dt. But in a circuit like this, we can actually write down using the Kirchhoff's law. We can have L di by dt, the voltage across this, plus 1 over C, the integral of I dt. So this should equal 0. is to say VL plus VC is equal to 0. So this equation, if I replace the I by the dq by dt, so that it takes this form, then I will have L d squared q by dt squared plus q over c is equal to 0. Because if we integrate this, we get q. So if we compare these two equations, then we are able to see that the following analogies apply. You have your mass, m, and you can see it corresponds to L, or the inductor L, inductor L. So the same way the inductors affect an electrical circuit, mass will be affecting the mechanical circuit in the same way. Of course, if you listen out, you will always be able to see how it applies. Like the inductor resists the flow of current. It slows down the flow of current. So when it comes to the mass, then because we are saying current and velocity are analogs in each of these circuits, then the mass would also slow down the velocity with which the system moves. That's how it becomes easy to appreciate some of the variables in one system if you understand how they affect the behavior of the system in another system. And then you can see that the distance x displacement x actually corresponds to charge q. Displacement corresponds to charge. Displacement corresponds to charge, and the spring constant S corresponds to 1 over C, or the reciprocal of the resistance. So S, spring constant, corresponds to 1 over C. So these are the analogies that we are able to obtain from here, which help us to appreciate how this system actually operates when we apply the force as and when we apply the voltage to the system. Remember, in our last lesson, we had also seen how the voltage and the force actually is the analogy of the voltage. So you can see we are building up the analogies, and this one really allows us to appreciate how one system behaves if we compare it to the other system. So the rebellion circuits would be adding a few things here and there, but for most of the part, most of the variables we have captured in this table. So let's look at the case of a damped mechanical system, and then we see what for example, would correspond to the damper. So if we add a mechanical damper, the speed U, we would compare this to this circuit where you have a resistor, still our inductor. You have R, then we have our C for the capacitance. So we have L, C, I. So if we write down the equations for these two different systems, then we would get M d squared x by dt squared plus Rm dx by dt. Remember, we have done this, plus Sx equal to 0. And for the electrical counterpart, you would have L d squared q by dt squared. We had derived this in our previous lesson, not previous lesson actually, but they're just the analogy above. We have written on the equation where we have the charge. So here we'll have we'd actually have L d squared, plus R dq by dt plus 1 over c q equal to 0. And you can see that the only variable that has come into play would be the Rm, which actually corresponds to the R. So you can continue building our analogy, because now we can see we can have in the table that we had actually drawn, we can have R M corresponding to R in the electrical circuit. And the remaining one, we can actually have the circuit which is having which is driven or forced circuit, so that we add the source. And if we add our source, then we have this. We have a circuit given by we have the mechanical circuit. We have the mechanical circuit given by this as because we have this, this, M there, and then we have the F, or F equal to F cos omega t, and I have the electrical circuit. We can have our source, so that we have this R C and the corresponding circuits for this would be, I will have M d squared x by dt squared plus R M dx by dt plus Sx equal to 0. Then for the electrical circuit, I will have L d squared q by dt squared plus R dq by dt plus 1 over c q equal to B sine omega. So equal to V cos omega. V sin omega is still, we can still have yes, V sin omega cos omega. That's what we are interested in the sinusoidal variation. But because here we have been using the cosine, it makes more sense if I get it to V cos omega t. And then now you can see the only new variable here we have brought is the source. So that the voltage in the electrical circuit is equal to the force in the mechanical circuit. So that part of the analogy had actually included in this particular diagram. I've done the force voltage analogy. So it is possible to continue studying this analogy. For example, what happens if we have our springs in series? What happens if we have our strings in parallel? How do they relate with their capacitors and the rest? So in this uh, in this particular presentation, we will not move into such a detail. We'll probably stop this analogy at this point in time. But what is important is that once we have these analogies, then we also want to compare the analogies with what happens in the acoustic variables. So let's just summarize what we have. Here are the mechanical variables. We have electrical variables. So we have seen you can relate the two so that you have the force F to correspond to voltage V. You have impedance Zm, impedance Zm, then this corresponds to impedance Z. Then we have the inductor, we have mass M corresponding to inductor L. We have the spring constant S corresponding to the reciprocal of capacitor 1 over C. Then we also see that if we have, let's say, a resistor Rm, then it would correspond to the resistor R. And also the velocity U corresponds to the current I. We have also seen that the displacement X will actually correspond to the charge Q. So we actually understand the correspondence between the mechanical and the electrical variables. So in our previous slides, what we are going to look at is the acoustic variables. But before we look at the acoustic variables, we'll look at the acoustic wave equation. What is it that makes the acoustic wave equation? And in the acoustic wave equation, uh, what we are going to find is that we'll actually be solving for pressure. But once you have solved for the pressure, what are the other acoustic variables? And how do they relate to the mechanical and electrical variables? So that will be the uh, uh, content of our next slide. The acoustic wave equation, how we saw the equation, and how do we relate the variables, so that we can understand the variables in the acoustic field. Since having those variables, it would be the moment we have the key variables, then we are able to evaluate the both of the things that we need, because we have known, for example, how we evaluate the power in the electrical circuits. So the same way, uh, the way we evaluate power in the mechanical circuits, and we are related the two. And then we also saw that they bear a lot of similarities, and you can extend this to the analysis of the acoustic circuits. And more importantly, we saw that if you have a system, it may be made up of all the three systems. It may be made up of the mechanical system, the electrical system, and with the acoustic system, like the speakers, the microphones. So we'll be able to appreciate what happens in the acoustic field, and it will also form the uh, background to the study of more advanced acoustic devices.